Welcome. Let's talk about uniform circular motion. First, just a definition term. Centripetal force is just a fancy way of saying net force towards the center of a circle. Anytime you hear centripetal force, that's just another way of saying net force, or at least the component of it towards the center of a circle. For what we're doing, it's always moving in a circle at constant velocity, so all of the net force will be towards the center of the circle. So this is kind of how things should always be if something is moving in a circle at a constant velocity. Its velocity is always tangent to the circle, so 90 degrees to a radius in the direction of motion. And your acceleration and net force is always towards the center of the circle. Always, no exceptions for something moving in a circle at constant velocity. So centripetal force, net force towards the center of the circle. If it's moving at a constant velocity in a circle, acceleration, net force always directed towards the center. Velocity is always tangent. Next topic. Love this formula. It's a gooder. So your net force is equal to your mass times your velocity squared, divided by the radius of the circle. That is it. Just make sure you can use it. There's a whole derivation to it. Khan Academy has a good derivation that I'll post on the Google Classroom. But it's probably too long for me to do it right now. This is also true. So F net is m times a, and this is mv squared over r. So if we divide both sides by m, we've got our acceleration is equal to v squared over r. You will be using this version more often, but this is also true, so occasionally useful. Another thing, this guy is very useful. Velocity is always just distance over time. Distance around a circle is just the circumference, or 2 pi r. 2r is the diameter. Diameter times pi is the circumference, the distance around the circle. And if you ever see like a capital T, that's not the same as little t. It has a special meaning. It is called period, or the period of time for, in this case, it to go around the circle once. Time to go around the circle once, distance around the circle. Distance divided by time is velocity. So, useful. Know this little substitution. This might look scary, but really it's not so bad. I'm just deriving this formula right here, which is a little ugly looking, but really you just have to use it. And notice how you come up with it is not so bad. F net is mv squared over r. That's the formula we're looking at just a second ago. And if we just sub in this formula for v, so everywhere there's a v, we just replace it with that, kind of our distance over time, distance around the circle divided by time around the circle, we get this. So we're just subbing in our formula for v. And then do a bunch of algebra, and we find this is also equal to our net force. So really you just have to be able to use this. This is one of your net force formulas along with mv squared over r. So m for pi squared r over the time to go around the circle once squared is a useful formula. Now, the big trick that you're going to have to do all the freaking time is you can come up with a formula for net force because of what's causing the net force. Could be gravity, could be big minus small, could be friction, could be gravity when you're at the surface of the earth, could be tension in a string that they just give you, could be spring force, could be whatever. You've done net force before, you know how to do it. So you'll have a formula for net force, and then just make that equal to one of these two formulas, depending on whether you know velocity or want to know velocity, you'd use this one. Or if you know the time around the circle, know the period or want to know it, you'd use this one. Because these formulas are what the net force has to be for it to be moving in a circle with those properties. If something has a certain mass and is moving around a circle at a certain velocity on a certain radius, it must have a net force equal to this regardless of what's causing it, whether it's a spring or friction or gravity or whatever. It just must be this, otherwise it wouldn't be moving in a circle like that. And same with this one. So our big trick is we come up with a formula for the net force because of what's causing the net force. So whatever that is, very situation dependent. Just look at your situation to figure out what's causing the net force. The net force must be towards the center of the circle. So that could give you a clue on what's the bigger force, or if you've got a big amount of small, or just what the net force might be. And then just make it equal to one of these two formulas, mv squared over r, or m4 pi squared r over t squared. So here's an example of it in action. If you've got this little pilot in a stunt plane performing a vertical loop with a 700 meter radius, it reaches a speed of 210 meters per second at the bottom of the loop. So we know velocity. So our formula for net force, because it's moving in a circle, will be the one with velocity in it. And we want to know the upward force in the pilot at the bottom of the loop. So here's my beautiful free body diagram of the pilot right here. And notice you've got gravity pulling the pilot down and the normal force of the seat pushing up on him, going up. And the normal force must be greater than gravity, because your net force must be towards the center. You can also think of it like, hey, if he's moving this way, you need a net force up to make him start to curve up. If this one was bigger, he would curve down instead, or if they were equal, he'd keep moving in the same direction in a straight line. So this must be bigger to have him curve up with the circle. So net force towards the center. So we just do our big minus small in this case. That is our net force because of the things causing it. Normal force minus mg equals our formula for net force, because it's moving in a circle like that, involving velocity because we know velocity. And then just plug in your numbers, move stuff around, and you're done. That is the gist. Normal force minus mg equals mv squared over r. Kick this guy to the other side, plug in your calculator, you're done. Here's a good example right here. If you're swinging something around, notice this is a view from above. So this is not a vertical circle, this is a horizontal circle. You're just looking at it from above. If you remember our initial drawing, acceleration and force is always towards the center. Velocity is always tangent to the circle. And so if you break the string, it's going to keep going in whatever direction it was going before, because an object in motion will stay in motion unless acted upon by a net force. Same direction, same speed. And so it'll go this way. It'll probably have gravity pull it down, but still it's going to be moving in this direction. All right. Thanks for listening. Hopefully this is helpful.